So welcome to this new Physics Matter colloquium prepared in the framework of the Physics for Development program and organized by the Forum of International Physics, so the FIP, at the American Physical Society. So first, I will introduce the member of our FIP panel. So my name is Christine Darf. So I work at the European Spallation Source in Sweden, and I'm the vice-chair of the FIP. So we have organized this series with members of the FIP Executive Committee, so which are Luisa Cifarelli from Bologna University, so in Italy, Joe Nimela from the ICTP in Trieste, Alan Hurd from Los Alamos Laboratories, and Marilena Longobardi from Switzerland, who is our FIP newsletter editor, and also for the website, you can find much more information from what we are doing on our different activities. So why physics matters? So the series was conceived in the middle of the pandemic. So thanks to Luisa Cifarelli's idea. So with several pre-recorded presentations with the purpose to reach and engage developing community. So with inspiring topic in the field of physics. So we want to promote international collaboration and to tackle the quest for physics curiosity. So especially supporting student and early career physicists. So you can find our website that collect all the different colloquia presented by renowned scientists, and it was launched in November 2020. So with by Luisa Cifarelli and by Paola Catapano, who is the head of the audiovisual production service. So for the CERN communication. So there is quite a nice connection as well, thanks to the little clip that will show you the purpose as well of this physics matter, maybe in a better words. So the science is a vector to transcend most boundary. If we think about gender, about religion, politics, so physics and science can generate a peaceful world. And it's the responsibility, our responsibility as scientists. So as a symbol, FIP has chosen the Sesame light source in the Middle East, which center of excellence has been built by scientists and for scientists driven by those values. So every month we propose a new physics topics with the scenery based on those 8 Middle East member country location with few intermission, so in the 18 observer country and international organization, for instance, like the one at CERN or in different area. So we can, or you can discover more of the earlier presentation by Sesame, for instance, by Andrea Lossi, the scientific director, who gave a nice overall presentation of the Sesame cell. And also last month's presentation by Guillaume Kamer, has been describing the new adventure of the Middle East women scientists. So it has been also followed by an exciting forum, with experts from different communities, sharing the experience on that topic. So for instance, with Galeb Natour from Jülich Physics Institute, showing the potential for students studying in different research infrastructure like the Sesame, by Bernard Amadi, who was emphasizing the possible synergy with or via physics and engineer without borders, and Zafra Lerman from the Malta Conference Foundation, explaining how science diplomacy can ease the peace, can enable peace and ease the peace in some sense. So the ingredient to build this united world of physics pass by a collaborative spirit and an effective transfer of know-how. So as for the Sesame, other research infrastructure and organization have captured the spirit. So like the ICTP, from which Nimela is depending on and working at. And there are also different research laboratory like Los Alamos or any places from which we depend that are also actors in all of those scenes. And I would like also to bring to your attention, the African strategy for fundamental and applied physics. So with the ASFAP community town hall meeting, which had gathered this week, many scientists encouraging and organizing a robust strategy aiming at limiting the scientific diaspora. So you can find as well through the Indico page more information, and there was a very good summary by Ferous Malek that shows as well the involvement from UNESCO, the African Union, and the different governance of those different countries. So now we can mention the African School of Fundamental Physics and the Application, so the ASP, which start next week as well. And as a common denominator for those two African activity organizations, so Ketavier Samagam, who is a senior scientist in Brookhaven National Lab. So I want also to mention, as a matter of fact, that today, so we have the honor, and we just spoke to Jim Gates as the ASP president, so who is now in the attendee. So beyond, so many engagement on the American continent and with the APS, so he strongly support the SFAP and the ASP, and he participated actually in the very first school organized in South Africa in 2010. So this school has been the opportunity as well. I mean, I had the opportunity to be the main organizer of it. So thank you, Jim, for attending this session today. So due to the pandemic in 2010, so the session that was supposed to be 3 weeks in Marrakesh last summer will be only starting next week. And then our lecture today, so Professor so Eliam Gross will present there the statistics physics, but today, so he will enlighten us and with the music of physics. So it's a bit more relaxing than the statistics physics, but it's still a lot of know-how that he will share with you. So how to use music as well and fundamental particles to compose our reality. So Eliam Gross, so he's a professor of physics in the Weizmann University, in the Weizmann Institute of Science. So I just recall that 6 laureate Nobel come from this institute, and also 3 Turing Award winner. So based on those different Nobel Prize winners, so we had, for instance, Adayona, who has been also a major actor in the Sesame initiative, so since 1997. So there I recall as well some presentation that Guillaume gave last June 15. So Professor Gross, so he's a lecturer also at the African School of Fundamental Physics and Application, as we mentioned. And actually his lecture was the preferred one by the ASP student in 2018, maybe because as well of the content. So after completing his army service in the elite communication unit, Professor Gross left to New York to study music. So there he became, he crossed across a cult books, the Tao books of Physics, which prompted him to come back to Israel and study physics at the Hebrew University of Jerusalem. So his master thesis at the Weizmann Institute was written on string theory after he deserted theoretical physics to experimental high energy physics. So in the last 20 years, Professor Gross has devoted his scientific career to the research for the Higgs particle and its discovery. So he was the ATLAS Statistical Data Analyzer Forum convener. So when it took the major part in developing the statistic method used to search and discover the Higgs. So he was then the ATLAS Higgs convener, at the time of the discovery of the Higgs boson. And as a matter of fact, I put as well in our Twitter the link from which Paola Catapano actually interviewed him just after this discovery. So I think it's an added value as well if you want to listen more about that specific moment. So now for the logistic as well from this presentation. So if possible, write your question in the chat box that you have and or raise your hand, but then maybe it's best if we will wait the end of the presentation to address them, unless so Eliam would like to make it more interactive and is agreeing to answer as well during the presentation. So now, so Eliam, I leave the floor to you.
Thank you. I opened the chat window. I like to be interactive in case you have questions, but I have to warn you, this is a very popular lecture, okay? Very popular. This is what I lecture in the APS is not this lecture. I really lecture about statistics and how you discover and how you set limits on things. But this lecture grew up because I gave in 2018, I gave a lecture on statistics to the APS, and the students had a lot of difficulties, and I was not tuned for the level. Now I know exactly what I need to do, but at that time I was not tuned, so I decided that I have to switch completely to something different. Then I took a lecture of mine, which I take music and use music to explain things also in statistics, and I gave it to them, and I think that somehow I found a way to our brain and heart. And since then, I'm invited to give it in many CERN schools as well. This is really funny. You'll see the lecture, you'll understand why I say it's funny. Okay, here is my lecture, and I share my screen. If there are problems, let me know. Please try again. Oh, why can't I share? Fail to start. Let's see. Oh, no. Am I allowed to share? Did you have to do
You
something?
should. Alors, wait.
Now I share. Can you see the screen?
That works very well.
Good.
Thank you very much.
Okay, wait a second. Just fixing all the windows here. Yeah, okay. So the picture you see on the left is actually me playing in the music studio of the NYU in the 80s, because the first thing I did before studying music is actually, before studying physics was studying music. But, anyway, so in this lecture, so I'm going to talk about strings, black holes, gravitational waves, matter, antimatter, Higgs discovery, and even path integral in quantum mechanics. So it's really about everything, but it's really from a different point of view. So it has gates. The first gate of the lecture is string theory, where I started my career in the 80s under the supervision of Nati Zeiberg, who's a very famous theorist from the Institute of Advanced Studies in Princeton, works with Witten. So the thing about strings is that it's beautiful because it shows that physics is about music, because what is string theory? In string theory, we go deeper into the matter, and the model claims that you won't find the fundamental particles, but you'll find the tiny, very, very tiny strings, really tiny, something like 10 to the minus 40 or something centimeter, 10 to the minus 33 centimeter, each string. So they're very tiny. That's why you don't see them in daily life. That's the model. We didn't prove it yet. And the thing is that there is only one string all over the universe, and this string vibrates. And the way it vibrates defines what particle it is. So it's like the modes of vibration of a guitar string or anything. So every mode of vibration is a different particle. So there's no more, you can't invent something which is more imaginary and more descriptive to say that actually the universe is made out of music. Now, the idea of string is actually that in particle theory, if you have an interaction between two particles, the interaction is local and point-like. While in strings, it's you have a manifold. You have something moves through a manifold and create tubes, and you don't have any local point where the interaction takes place. And that's what allows actually to put together gravity and quantum theory with no problem at all. Now, in 1985, there was a big revolution in the string theory. The string was invented in 1987 or something like this, 85 even, something like this, by John Schwartz and Michael Green. But the big revolution became in 1985, because by that time, by 1985, they had 5 different string theories, and they had no idea where they go with it. And the string demanded that there would be at least 10 dimensions to space-time. And then came Ed Witten in a lecture at University in Santa Cruz, I think, really pioneering, one of the most memorable lectures of all times. He said that actually, if you add to the 5 string theories another one, which is actually supergravity, 11-dimensional supergravity, what you find out that the basic structure is not a string, but a membrane. And strings are really 1-dimensional slices of 2-dimensional membranes vibrating in 11-dimensional space-time, which is crazy. And he called it M theory. I mean, never explained what is M. Nobody knows what is M. Some people call it magic. Some people say membranes. Some people call it mystery. Some people call it monster. Some people call it mother theory. Nobody knows, but all of the names actually suit what it is. But the idea of Witten actually is that all the string theories are actually one theory, and you can actually, by duality, move from one to another, and there's not more than one string theory in the world. They are all connected, and like in music, like you're doing music in modulus, where you can go to all the scales in physics. You can go to all of them, and Bach showed us how to do it. You can actually go from one model to another, and all the models are the same. This is all about music in a way. Can you hear the sound? Can you hear the sound?
Yes, we can.
So here in Bach's Prelude, you go over all the scales in one go, and you show that everything is actually connected. You go by fifths. So fifth is like the duality in string theory. You go from one theory to another, and they are all actually the same theory, like different scales, but same theory. Think that every time she changes the scale, it's like you skip to another string theory. So, I mean, this guy, Tim Blay, he has a YouTube site called the A Cappella Science, which I'm sure that all of you know. And actually, he has songs which are very sophisticated about everything. He wrote a song about the Higgs discovery, which is fantastic. And this time he takes Bohemian Rhapsody of the Queen and he tells us what is string. So let's hear a part of this and get some idea.
Is string theory right? Is it just fantasy? Caught in the landscape, out of touch with reality. Compactified on S5 or T star S3. Spaces of pure void. Why should it be stringy? Cause it's quantum plus classical, non-renormalizable. Any way you quantize, you encounter infinity. You interact via paths we understand, using Feynman diagrams. Often they will just rebound, but now and then they go another way. Quantum infinities will make you cry unless you can renormalize your model of baryons, fermions, and all other states of matter.
So you can go afterwards and listen to the whole of the song. It's really fantastic, so fantastic that Brian May, who's also an astrophysicist, he got his degree after in an interview in London. He said to the reporter that the dream of his life was to become a doctor of physics, but he never managed to do it. So he was contacted by a professor of astrophysics, suggested that he does his PhD with him, and he did it. And he even wrote 2 books about astrophysics. He was a chancellor of a university. Brian Green, the guitarist of Queen, said to him, you know, your arrangement on that video was just fantastic. So he said to him that this arrangement of Tim is actually the closer that anyone else did to Bohemian Rhapsody. So I think that this is really fantastic. So that's about strings. But if we talk about strings, one answer that the strings is claiming to give is to the answer to the question, do we need a creator to make the Big Bang? And in string theory, if you believe the membranes theory and all this M theory, etc., so big membranes can collide, and there are infinite number of members that collide every second and create big bangs. And actually, you don't need any creator to do it; it just happens all the time and since ever. So principle what we know, and that's not a model. We know that in the beginning there was energy and there was actually a Big Bang, that we have proof for this in a way. We claim that the Big Bang is in a Goldilocks zone. What does it mean, Goldilocks zone? Where does it come from? The idea is that it's not too fast and not too slow. Imagine the Big Bang was too fast and all the galaxies, or all the material will go tear apart, and there wouldn't be galaxies, no nothing, and we wouldn't be here. Now, if it was too slow, then what would have happened? That gravity would suddenly pull everything back to the origin, and again, all the bang will actually diminish, and we won't be here. So it was exactly in the right spirit, the right speed, not to be too fast and not to be too slow. So it allows the creation of galaxies, and then evolution, and then the creation of life. So the Goldilocks zone came from the story about this little girl named Goldilocks, which went and tasted 3 different bowls of porridge of the birds, of the family birds, and finds that she prefers the porridge that is neither too hot and too cold, neither too hot nor too cold, which belong to the little bird. And she sits down and drinks it, and it's a very famous children's story. So that's why the name Goldilocks zone means that you are just in the right position, and not to have, just in the right magical position that things happen. For example, the mass of the electron is not too heavy and not too light, and that allows the atom to be not too big and not too small. And actually you need it to create life, to have chemistry as we know it, etc., etc. So there are many things that happens with this miracle. We call it fine tuning. And how do we solve the problem of fine tuning? That we solve it in physics by actually the idea of the multiverse, which also is a result of the M theory. But what determines if the Big Bang will be fast or slow is actually initial conditions. You have a formula that describes the Big Bang, but there are initial conditions. Initial conditions are very, very critical to the development of physics state, okay? Initial conditions. So let's demonstrate what is the initial condition. I'm sure that you identify this one. I'm sure that you identified, and you just ta-ta-ta, that was enough for you. You didn't need more than that. That's an initial condition. And you know that it's Beethoven fifth. We can try another one. I'm sure that all of you identified it by that time already. That's Richard Strauss. So spoke Zarathustra. And the last one, let's see if you can identify it by initial condition just on the spot. You can test yourself. There's, of course, Mozart. And that brings me to the question, do special initial conditions indicate a master plan? Of course, this is a basic question. So if we take Mozart, for example, is Mozart a result of a master plan? So the answer is not really, because in 1800, when Mozart lived, the world population was about 1 billion people. The probability that a genius like Mozart will be born, even though it's small, when you have 1 billion experiments, 1 billion people, one of them is bound to come out as Mozart. It's not so rare, okay? There have probably been more than one Mozart, and they are born even today, every day, but they don't go to music. They make companies like Apple, or like Microsoft, or like Netflix, or like Amazon. The genius of today, they do different things. So if we look at the large-scale picture of the sky, deep picture of the sky, we see actually that there are 100 billion galaxies times 100 billion stars. So this is a huge number. So the fact that in one of them, there is the conditions, the right initial conditions, and so life can emerge, and so one star, one system has a sun, and the Earth is not too close and not too far from the sun. If it's too close, it will be too hot, it will be burned. If it's too far, it will be too cold, there won't be life. And also the Earth surrounds the sun in a kind of circular orbit and not elliptical, because if it was elliptical, it wouldn't be here, because at some place it's too close, some place it's too far. All these things look like miracle, but when you have so many stars, the probability that one of them will just by accident fall in the right place is not so small. This is what we call the look elsewhere effect. I mean, if you take everything into account, it's bound to happen at one time, sometimes at one place, etc. So I don't think initial conditions are a result of a master plan. For example, you can ask yourself if a monkey can type, which types writes a meaningful sentence. One monkey won't do it, but you have a billion monkeys. One of them by chance will write something that makes sense. So it's plausible to think that in one of billion galaxies, there will be one with the condition needed for life creation. Now, string theory, M theory, goes even further than that. They talk about multiverse. They talk about the fact that our universe is not a special one. There's no reason to believe that our universe is special. There are something like 10 to the 500 universes. So who pushed the button? Is there a need to push a button? So as I said, string theory with membranes gives an answer to that as well. But the philosophy will still remain, because I don't see in the near and not in the far future a possibility to put string theory into a real experimental test. Which brings me to the idea that actually the Big Bang started in a singular point, like a black hole actually. So let's first let's see how can we see a black hole, and let's actually remember what is a black hole. If you take Earth and you shoot a missile through it, you need to give it a speed which is more than 10 kilometers per second, which is used about 30,000 kilometers per hour. So it will have the escape velocity and won't be trapped by Earth's gravity, like throwing a stone without it falling down. You need 11 kilometers per second, something like that. That's when the radius of Earth is 6,500 kilometers. If we now squeeze Earth with the same mass, but larger density, because we keep the mass, to a dimension of 65 kilometers, the escape velocity will square to 100 kilometers per second. If we squeeze it now with the same material, with a very huge density, it will become huge density to the size of a little marble, say, third of an inch, then the escape velocity will be close to the speed of light. And when the escape velocity is more than the speed of light, light cannot escape, and that's when we get a black hole. Now, this idea is explained by Einstein's model of gravity, which talks about effects that gravity is not actually a force, but it's a curvature of space-time. So the idea is that in the beginning, say, space-time was flat. So everything went smooth in the right directions, etc., etc. But then you put a higher mass, very massive sun or something, it bends the space-time, and the space-time curves, and there's nothing above or below. It's just the illustration here. There's nothing above or below because this is space-time. And then if you put a star, it goes on the path, the natural path of it to go on the space-time is by ellipses, because it cannot go anywhere else. And Einstein's equation says that matter tells space how to curve, and space tells matters how to move. I should have used actually space-time. Matter tells space-time how to curve, and space-time tells matter how to move, and that's how we discovered it in something like 1919. There was an eclipse somewhere in two places on Earth, in America and in Africa. And there was and if you look here in if we have a star somewhere here, then the light of the star is curved by the curved space-time. And when we observe the stars, we see it in a different place than the original star, we see this deviation and we know that you are right. And that's how the model of Einstein, that gravity is actually a curved space-time, was proven to be correct. Now, if a mass heavier than 10 sun masses, it curves space-time such that the light cannot escape. And that's actually the idea of a black hole. So how would you see a black hole? The idea of how to see a black hole was explained in a magnificent way with music by John Wheeler, who was actually the supervisor of Richard Feynman, for example, and many other very, very famous physicists. But Feynman is my mentor, and Feynman was great in giving lectures like this. And he said, imagine that you're in a ball and the bride is dressed in white and the partner is dressed in, the groom is based in black, say, black tuxedo, whatever. I couldn't find the right figure, so I used these ones. And then they dance and somebody dimmed the lights. What would you see? You would see the bride dancing around nothing.
Dance me to your beauty with a burning violin. Dance me through the panic.
The Nobel Prize of 2020 was given to Roger Penrose and a team of 2 physicists, 1 American, 1 German, that Roger Penrose from proving that a black hole comes out of Einstein's equations, as I showed you, by curved space-time. And the 2 groups, the American and the German groups, proved that by this picture, this is one of the group working on the European Southern Observatory, that proved that actually there is a huge black hole in the center of the Milky Way and actually in the center of each galaxy. So this is the way they discovered it, exactly by the idea of John Wheeler. Now, black holes is a fascinating story, because how will you discover black hole? How would you see or discover black holes? So 5 years ago or something like this, the LIGO experiment, also in the United States, managed to probe 2 black holes dancing around each other, because if the idea of space-time, of curved space-time is correct, and probably it's correct, then when 2 black holes are actually going one around the other, forms a binary star, say, so they will actually perturb space-time and create whirlpool in space-time, as you can see here. You see the whirlpool in space-time, you see it. And the frequency becomes, as they get closer, the frequency becomes bigger and bigger. At some point, it's actually audio frequency, like from 20 hertz to 10, 20 kilohertz. And I saw a demonstration of it in ICHEF, where the guy proved it with the driller. Look. Here's a stroboscope.
I can visualize it as well.
Let's do that the black hole.
You see that this spiral shape is not very special.
So what happens is that first the frequencies you can see below here, as they get closer, they become bigger and bigger, and then it gets to frequencies which are like audio frequencies that you can hear actually. You connect it to a speaker and you can really hear it. And then it calms down. So when you connect the signal to speakers, you can hear it. Because when it comes to Earth, you won't really feel it. When the gravitational wave comes to Earth, it actually distorts Earth in this way, but this is really exaggerated. The distortion is the size of 1 over 1,000th of the radius of a proton. So there's no way you will feel it, but you can hear it.
not what you have heard chirps sound like, right? But that's because this is relatively low frequency and very, very short. But it is what the data that is shown is looking like. So to make it easier for the human here, even though we can hear this, but to make it nicer, if you want, to make these black holes really sing, we have shifted the data, the frequency of the data to higher frequencies. Again, you heard it 3 times. It's the same data, except that now we have shifted the.
Now the thing is that what you are supposed to hear is the frequency that becomes tighter and tighter. Whoop, whoop. So this guy, Alan Weinstein, who was the physics coordinator of the analysis of LIGO, gave a lecture at Weizmann, and I saw him making 200 physicists, 200 professors full of themselves, and I recorded it, so I'm going to show it to you.
Low frequency, a thud at the very end. Did you hear that chirp at the end? You did? It goes like this. It goes like this. You do that. Low frequency. Hey, let's start. Hey, everybody. Now, very good. You hear that little at the end? Okay, that's probably a voice cracking, at least my voice cracking. Actually, that's a black hole cracking. Okay, it's a little different thing. Okay.
And this discovery 4 or 5 years ago actually ignited the imagination of many musicians. One of them is Arthur Jeffers, but I'll show you another one after that. So he wrote a whole electronic music piece about the discovery. This chirp is really inspiring. The thing about it, that this is really music that the universe plays to us. Now, I met on an ice skating in Princeton, this guy, Eilam Gross. It turned out that he was asked to write some music for NASA for some occasion to celebrate 100 something years to Einstein's general theory of relativity. And he was really inspired by this black hole dance, by the dance of the black holes. So he wrote a piece, and first I thought that he's bullshitting me, I'm sorry for saying it. And then I put my earphones and I listened to it, and I was kind of, wow, and that was amazing. So let me play you 2 minutes of this. Couldn't stop it. Undoubtedly inspired by Odyssey 2000, Stanley Kubrick. Anyway, so in the old days, there was another way to see black holes, because when there is a merging of a star into a black hole, a star is actually made of gas, and then the gas can be absorbed into the black hole, but then the friction creates can create an explosion, and where you get two jets of particles which can extend to hundreds of thousands of kilometers. And if you have the right telescopes, the right telescope of all sorts of light, you are able to observe these jets. For example, in this picture, you need the radio emission telescope, X-ray Chandra, and optical and UV by Hubble, etc., but you can actually see the jets when a black hole creates a collision. Now, in order to demonstrate the need of all sorts of telescopes to see things, we can also use music. And the idea is the following. If I take the Crab Nebula and look at it in various spectrum of electromagnetic waves, so this is the Crab Nebula. And first, let's look at it with the radio waves, and that's what you will see. Same thing you look at with infrared. Same thing you look with visible light. Ultraviolet. If you go to X-ray, you can penetrate actually the middle. And with gamma rays, you can actually watch the core of the nebula. So in order to demonstrate this, what is the meaning of all these different telescopes, I decided that we can actually look into the piano. So I can look at the piano, and I can look at the piano as if I have a low frequency here and high frequency here, and I play only octaves of different octaves, each one represents a telescope, and see when you can identify the very famous thing that I'm playing. So let's start with the radio waves. I mean, very, very low frequency. It's coming. Got it? Let's move to infrared, 1 octave higher, and see what happens. Each telescope, each range discovers new things in music. If we go to visible light, we'll probably identify the piece. If anybody identified it and he didn't hear me before, let him write down in the chat what it is that he hears. Okay. Let's see if you can identify it now, but I'm almost certain you will now. ultraviolet.
Ready.
Now you got it. So we can move to X-rays. That's of course Scott Joplin, the entertainer. Let's hear all together. Yeah, so if I take all the telescope, all the 5 telescopes together, I can actually see everything. I can see the radio waves with the very large array in red, the infrared in yellow, the Hubble visible in green here, around here, the ultraviolet in blue, with Newton as you penetrate inside, Chandra X-ray in purple. So this is like playing the whole piece of the music when you can hear and see all the notes. When I visited this NICHF lab, it turns out that there were partners in building Ligos Mirrors damping, because the whole thing about LIGO, that there are mirrors there and they have to be very, very stable to high frequency vibrations. So that's when I realized that the idea that they're using is that when you have overtones, high frequencies, the duplications of frequency with higher and higher duplication, like ×2, ×4, ×8, ×16, then actually you can actually keep the basic frequency very, very stable. So if what are overtones? Let's hear the overtones here. So you see here the guy, the same guy who showed us the black hole dance, demonstrate the idea of the overtones in keep the mirror very, very stable.
So you try pendulum in 2 seconds. It's also a vertical oscillator, a non-spring system, also around 2 seconds in periods. Okay. The funny thing is that above the resonance frequency, text is a vibration isolator. For instance, if I move now 10 times faster than the resonance, which is 5 hertz, I can see I can move my hand almost half a meter.
This is fantastic, isn't it?
It's moving only half a centimeter or so. So that's a factor 100, and this factor 100 is exactly what you expect if you look to the equation of motion of a mass spring system.
Then I realized that when you talk about overtones, one cannot not remember.
You're not doing it now.
The fantastic Richard Feynman. Last journey that never took place to Tuva. Actually, I heard the story from a friend of mine, Glenn Cohen, who is the guru. He wrote a book also, The Guru of Statistics of the LHC, undoubtedly. And Glenn told me that he was a very good friend of the son of Layton, who wrote with Feynman one of the red books. And one day, Feynman talked to Glenn, and Glenn told him that he collects stamps. So we asked him, you collect stamps? Do you know where is Tuva? And Glenn didn't know the answer. Feynman never made it to Tuva. Tuva is some canton, some crazy canton in Russia with near Mongolia. But Feynman was fascinated by Tuva because they have something called throat singers there who can actually sing from the throat overtones. Let's hear it. I learned it from Feynman. So if I don't tell you new things in physics, obviously these things are new to you, I'm sure. Feynman, let's complete the story of Feynman, that he had a van, and in the van he had pictures of Feynman diagram. So one day somebody stopped him and asked him, hey sir, why do you have drawings? He wanted to show that he's a smart student, smart guy. Why do you have drawings of Feynman diagrams on your car? He said, yeah, because I am Feynman. Anyway, so the Feynman diagrams brings me to the subject of symmetries. There's a lot of symmetries in Feynman diagrams, and you can calculate many diagrams using symmetries. So that brings you to the fourth gate, which I call it symmetry in Amadeus. If you look at the Taj Mahal, there's obviously a mirror symmetry here. If I change right and left, I actually get the same picture. Well, because of the lighting, it looks different, but it's the same thing as you can see here. And Leonard Bernstein gave a fantastic lesson of symmetry in, I show you 1 minute of it, but we can apply it to physics as well.
Now this theme begins with the chain we've already discovered. And this phrase, which is 2 bars long, is immediately countered or answered or mirrored, if you will, by a complementary 2-bar phrase, thus producing a symmetrical 4-bar structure. But this double phrase is clearly incomplete, and so we find it followed by its counterpart, another 4-bar phrase, which is reducible to a similar pair of 2-bar phrases. Now, the theme is now balanced, as you can see, and if I were more pedantic and more cruel, I could have made this musical deep structure even longer, but in any case, here it is, a perfect nightmare of symmetry.
Okay, so in the movie of Amadeus, they demonstrated how Mozart was actually using the symmetry of going forward and then backward, forward and backward. And many situations in physics are symmetries. Actually, we know that all conservation laws are a result of symmetries. So let's have a look at how in Amadeus they explain the notion of symmetry.
Mozart is not here.
Stop it!
I am.
Stop
I am
it!
stopping it.
Stop it!
I am stopping it. Slowly. There. You see? I've stopped. Now we're going back.
No!
Yes.
No!
Listen, you don't know where you are. Here, everything goes backwards. People walk backwards and dance backwards and sing backwards and even talk backwards.
That's stupid.
Why? People fart backwards.
Oh, ha.
So I'm sick. So I'm sick.
Yes, you are. You are very sick.
No, say it backwards, shitwit. So I'm sick.
So I'm sick.
So I'm sick.
Sick. Kiss my jaw. Kiss my ass.
Emeram.
No, I'm
Just
not
say it.
playing
It's
this
serious,
game.
Emeram.
No.
Say it, you'll see, it's very serious.
Ram. Marry. Oh, I'm not going to marry you.
So the same symmetry exists when we talk about matter and antimatter. So we expect that as the universe is created, actually, from the Big Bang, we'll have the same amounts of matter and antimatter. And as you know, this is not the case. Somehow antimatter got lost, and lucky for us, otherwise we wouldn't be here. But symmetry was broken. What does it mean, a breaking of symmetry? A breaking of symmetry is demonstrated in every piece of music that has symmetry, including Mozart. So you see that the infinite part of the music comes when it goes out of the symmetry. Suddenly he changes the scale, suddenly it goes to a different note, and then you pay attention and then you realize that something is happening there. So the mother of all symmetries broken is, of course, the Higgs boson story. So I'm going to spend some time on this. So the Higgs boson story is all about curiosity-driven science because it tries to answer many interesting questions, like why do we exist? Like what are we made of? Like how did it all begin? Or what's the fate of the universe? All is related to the Higgs boson and the mass of the Higgs boson. Now, the answer given by the Bible, you all know, in the beginning, God created heaven and the earth was without form, etc., etc. The answer given by Peter Higgs in 1964 is this 3 pages letter in which he writes this sentence here. It's worth noting that an essential feature of the type of theory which has been described in this note is the prediction of incomplete multiplet scalar and vector boson, which means he predicts that we should discover something new while searching for the Higgs. Now, in 1964, Higgs sends this paper to physics letters, and it's rejected. It's rejected, so he has an epilogue to the paper in which he puts this sentence. It's worth noting that you should find a new particle there, and he sent it to Physics Review. The referee was Nambu, and he told him that he will accept it to publication as long as he also cites Engler and Brown, who sent a paper 1 month ago about a similar subject. Now, I had some correspondence with Peter Higgs, and that was before 2012, before the discovery of Higgs. It was for the purpose of all these popular lectures that I gave. And I sent him many, many questions. Actually, I went to Scotland to meet him. And the night that I arrived there, they put me in one of the bed and breakfasts there at Edinburgh University, and I gave a seminar about Higgs statistics the next day. That was before the discovery. But then I get a telephone call as I arrived to the hotel, and he says, Eilam, I'm sorry to tell you, Mr. Higgs, Professor Higgs told me that he cannot meet you because he has to babysit his grandchildren. I was in a shock, and I mean, I made all the trip just to meet him. And I insulted and humiliated. I went back home, and a whole year after that, I get a letter from him in which he answers by handwriting every bit of question that I asked him. And in one of them, he says that, why is this? Yeah, in my second paper, I use Lagrangian field theory, etc., etc. So the massive spin zero boson, the Higgs boson, was an obvious feature to which I drew attention. So he claims the fame by telling that he is the one who predicted the Higgs boson. And it's true, Engler and Brown did not predict the Higgs boson, and they actually were more into the mechanism. The idea of the broken symmetry that predicts the Higgs boson was of Peter Higgs alone. Leon Lederman wrote this book, The God Particles, in 1980 or something like this, after about 15 years of searching for the Higgs in Fermilab and not discovering the Higgs, and they were frustrated. After 15 years, they were frustrated. It took us 50 years, not 15, 50, 50. But he wrote a book after 15 years, and he wanted to call it the goddamn particle, the one that we cannot find in search. And the publisher told him, listen, the goddamn particle doesn't sell, call it the God particle. That's one of the stories that Leonard Lederman tells, and actually he tells the story after the discovery of the Higgs boson. So I'm not sure I believe this story, because until Lederman said that this is the reason he called it the God particle, I used to explain to people that the God particle is a very poetic and good name because the Higgs gives mass to particles, but that allows our existence. So there is some sense in calling it the God particle. Never mind, whatever it is, the golden particle, the God particle, it was discovered in 1912. And all the idea of the God particle is that it is the mother of all symmetry breaking. This is actually the little man on top here, is the universe, and that's the potential in which the universe exists as the universe was created. It was very, very hot, so the little man in the universe was sitting on top with the very hot bottom, and he finds his way. He couldn't move anywhere because it's so hot. But then the universe gets cold, and then he will fall down to the valley. But there are infinite places in the valley he can fall off. Which one he will fall to? So this is the spontaneous symmetry breaking, that he can fall to any of them, and then the beautiful circular symmetry will be broken. But there are infinite possibilities. In string theory, each one of the possibilities is a universe. In our universe, it fell somewhere here, and this is our universe. So in the beginning, there was the Big Bang, as we said, and the Higgs field. The Higgs is actually a field. A particle is actually a perturbation in a field. A field like electromagnetic field, something that is all around us. And the Higgs field moved upon the face of the universe. So let's explain the Higgs field. So this is the universe, and that's the Higgs field. And this woman is like a particle. She tries to move in the universe, which is filled with the Higgs field, and it's very difficult for her to move. That's what gives her mass. Now, if you look at these creatures here, you see that they try to move, and the heavier the particle, the heavier the resistance of the particle to move, it gets more mass, and this is actually how the Higgs mechanism gives mass, by actually interacting with particle. It interacts with particle and gives the mass. The more it interacts with particle, it gets more mass. So this is what you see here. And it all happened about 14 billion years ago. And once the Higgs field was there was a mass, and how do we try to find the Higgs field? Actually, we try to create the Higgs particle by perturbing the Higgs field that's around us. So we have a collision, and from this collision, we actually try to perturb the Higgs field and actually generate and create the Higgs particle and discover it. Now, a collision event looks like this. This is a Higgs which reincarnates. The Higgs doesn't live long, it decays immediately. This Higgs decays into 2 photons, and we try to reconstruct the 2 photons. Here's another Higgs decays to 2 photons. Here's a different Higgs and a different one. All of them looks the same, but they are not the same. All of them Higgs decays into 2 photons, but they look different. So we have a huge statistic of Higgs decaying into 2 photons. And now we want to discover it. So how do we discover it? So let me explain how do we discover a particle which creates a little excess in some point here, very, very little, which is very hard to detect. And let me use music to do it. So here we count actually the number of collisions that gives us some mass. To each number, I actually attach a note. So let's first see what would have happened if we have no Higgs. So the background would have been smooth, and it will look like this. And it will sound like this. We can also code it by colors, high frequency, low frequency. We can combine them. There was a Higgs. Did you notice? There was a Higgs. Sounds different, right? Something that is very difficult to detect sounds. Now, the problem is that it doesn't look so smooth like this. There is noise. This is, for example, a TV static noise, which, by the way, hides inside it also traces of the Big Bang. We won't go into that. So using this idea of frequency, let's try to understand how noise looks like. So here you have a central frequency and some noise with which actually goes around it. The noise have a Gaussian distribution, and most of the time it's between what we call plus minus 1 standard deviation. 68% of the time is between 1 standard deviation. Now, the problem with the noise is if you dress the smooth curves that I showed you with the noise, it's very hard to identify the signal. Look. By the way, the Higgs is here. The noise hides it, completely hides it. do we get over this? How do we overcome the noise? So we have to understand, first of all, that we're talking about a Gaussian distribution, which looks like this. For example, what is the meaning of a normal distribution? This is IQ distribution. 68% of the people have an IQ between 85 to 115. So it's 100 plus minus 15. It means that one standard deviation of this is 15. Very low percentage of people, 0.1% will have an IQ of 145. So this is very, very rare. Or a very low IQ, of course. Very, very rare. So you see, if I try to see when I have a noise, what is the frequency of one standard deviation, and then of 2 standard deviation, 3 standard deviation, I see this. Most of the time it's between plus minus 1 sigma. Time to time there is a noise. Go to 2, 3 sigma. Got the point? So it's very rare. It's very rare to get a noise which goes above 2 or 3 sigma. So let's look again and now. This is the noise, 2 sigma. Very rare to get something that goes below 4 sigma. Actually, you have to do at least 10,000, 1,000 to get, say, 3 sigma, 1,000 trials, or 10,000 trials, or 100,000 trials to get a 4 standard deviation, and 10 million trials to get 5 standard deviation. So this is the normal background plus noise. See, it's very hard. You won't get here. You see, when you look at this like this, you see that you never go below 2, 3 sigma. People say, how can I actually tell the Higgs from the noise? Just collect more statistics. You need more collision. Because if you multiply by 4, you take more collision, the signal and the noise, they will multiply together, then the significance, which is the significance is how many, how significant is the signal over the noise. So we actually quantify by S over square root of B. The signal over square root of the noise will increase by a factor 2. But if you take 25 times more data, the signal over the square root of the noise with the significance will grow up by a factor 5. So as you accumulate more events, at some stage the signal will emerge on top of the noise. So this is why we need to take a lot of statistics in LHC, because the signal is very, very small and you want to overcome the background. So this is simulation of the Higgs after 2 years. This is what we expect to see by simulation after 2 years before we did the experiment, before. So you see. This is simulation. Which means that after 2 years, if we take data for 2 years, if there is a signal, we will see a 5 standard deviation fluctuation, which is very rare if there was no signal. Very rare if there's no signal. There is a signal, we will be able to see a significance of 5 standard deviation, and that's the magic number. You need 5 standard deviation, which is very rare if there's only background, to declare that you have a discovery. So here's real data. Let's see, here's real data with a 5 sigma. Let's see if you can hear the Higgs boson with the real data 2012. I'm sure you heard it 2 times or 3 times. So let's see what's happening here. So there is something here, there is something here, something here. Obviously, the one here is the bigger of them all. So now let's see with the standard deviation what it tells us. So we have a discovery. That's the Higgs discovery, the real Higgs discovery. So this is the famous picture from ATLAS that you see. And what we do now is, in order to see clear the signal, we take from the data, we subtract the background, we subtract it, and then we get only the signal. Only the signal, and it's very, very clear. It looks like this. Okay. That's music. Eureka. So a paper comes out, and if you look at the paper, now you understand the two figures that you see in the paper. You understand the bump here, and you understand the meaning, and the more important, I hope that with the music now you understand the meaning of this actually peak here of 5 standard deviation. So if the Higgs gives mass, where did the Higgs come from? What pushed the button that started the Big Bang? The question is still there, so you can call it the God particle, but you still need the God to create the God particle unless you buy all the ideas of string theory, and then you don't need to look for a reason because it's there already. Now, 2 guys from CMS actually did the same trick that I did. I discovered it after finishing my work, and they did it with real music, but now I have to show it, right? See it again. Right. Let's go to the last gate, the last part of the lecture. I call it the spiritual world of the quantum, and the idea came from a book by Stefan Alexander, which is called the Jazz of Physics. And he bends the music very much to match the physics, but this one is so nice that I couldn't just skip it. And he's talking about his favorite jazz composer called Ornette Coleman, who invented some abstract jazz, exactly the jazz that many people don't like, but when he explains it, it becomes so interesting that I spent an hour listening to it to try to find the patterns that he's talking about. It's not always as beautiful as this, as we will see in a second. So many of you know the double slit experiment. And the idea is that when you have 2 holes and you shoot a particle to them, they will either hit the left hole or the right hole. So you'll get a pattern of 2 lines. But not when it's a quantum particle, not when it's a photon or an electron, a particle with the size of the atom scales.
Instead of the 2 vertical bands that you'd expect, a series of vertical smudges appear. To make sense of this pattern, you need to look at it from the perspective of a single photon. This photon is landing in a place on the back wall that would be physically impossible if it were traveling straight through just one of the slits. So, the only explanation is that the particle has gone through both slits simultaneously. By the time it reaches the back wall, it has come together again as one photon. Multiply this single photon 1,000-fold, and you have the distinctive pattern that Mark saw. Think about it. A photon arrives at the slits in a hell of a quantum state and travels through both. A single object is in two places at once.
The only
Now
way
you're blowing my mind.
Good. That's our job to do, to blow people's minds. So make you think.
So the only explanation is that when you shoot a particle, a very, very small, a quantum particle, to a double slit, it somehow goes through both slits as a wave and then materializes itself again and appears in one of the possible interference patterns of a wave. Now, I don't have time. This is a whole lecture to talk about quantum mechanics, but this is very known phenomena from wave theory. And the idea is that there are no actually particles. Particle is not a real thing. The real thing is that all particles are actually wave packets. And the electron has a wavelength of about 1 nanometer, which is about the size of the hydrogen atom. The wavelength of a particle is uncertainty in the location of the particle in a way. So this is why particles actually behave like waves. So now let's do the following idea. Let's use a source of light and shine through two slits. So the pattern, you know, the pattern is that the idea is that actually, so give me a second. Okay, so what happens here? Okay, I want to show you. So the idea is the following. The light goes through both slits. And when a peak of a wave meets another peak of a wave, you get a highlight here. When the peak meets the low of another wave, you get a zero, a dark. So that's how you get dark spots and very high intensity spots because of interference. So it's all about superposition of the wave that comes from here and the wave that comes from here. So what you'll get is a pattern of light, dark, light, dark, light, dark, light, dark, etc., etc. When the top of one wave meets the top of another wave, you get a high. And when the top meets the low of another wave, you get a sort of a dark spot. And this is an interference pattern, and you all know it, and that's the way we do it. Now you see it also with sound. If I have two speakers and I play a frequency through both speakers and I move around, I see the interference pattern. Listen to it. Low, high, low, high. This is why when you connect your stereo speakers, make sure that the polarity is the correct one, otherwise they'll cancel each other. Now the thing is that you can also make 3 holes, and you will still get the picture of interference pattern here. You can make 3 holes, you can make 4 holes, you can make 5 holes, you can make 6 holes, you can make as many holes as you like, and you'll always get here the interference picture. So you can take the screen and actually make as many holes as you like, you'll get the interference picture. Actually, you can take the screen and make an infinite number of holes in the screen. I call it a Zen screen. If it has an infinite number of holes, it's not there. But still, what you get here is a superposition of all the possible paths that come from here to here that goes through the screen, the virtual screen that does not exist anymore. So when I look what happens here when there is no screen, I actually do see the superposition of all possible paths that go through this virtual screen here and arrive at this point here. More than that, I can add another screen and make infinite number of holes in this other screen. And I can add another screen and another screen. So actually the space between the light source and you is full of infinite number of screens with infinite number of holes. So, which means this is exactly the idea of Feynman's path integral, which means that when a particle, this is the path integral, if you put an infinite number of screens and drill an infinite number of holes in each space, we conclude that even in empty space, when a particle goes from a point S to a point O, it's actually it goes through all possible paths. And what you see is actually the combination of all possible paths that go from one place to another. This is a fantastic idea. When you start here and you end there in physics, what you see there is the result of all possible paths that you can take from here to there. This is a mind-blowing idea. And you cannot contradict it. This is the way it is. And Stephen Alexander thought about it and said that it reminds him of Ornette Coleman with his music. But then I Googled Ornette Coleman, I found that he said the following beautiful sentence. If you want to be a great musician, I'll play you Coleman in a second. You understand what I'm talking about. If you want to be a great musician, you need to know three things. First, you must master the rules before trying to break them. Second, music is about tension and resolve. And third, practice, practice, practice. But when you're out playing, forget it all. So just replace the word musician by the word physicist. If you want to be a great physicist, you need to know three things. First, you must master the rules before trying to break them. Second, physics is about tension and resolve. And third, practice, practice, practice. But when you give a lecture, when you're talking, when you present your stuff, forget it all. So the idea of free jazz, the style of Ornette Coleman, is that I have a starting point and I have an end point, and I'm trying to go through all possible paths from the beginning note to the last note. I could do it in a sequential way, and then it will sound very, very nice, like I played to you in the beginning, but I can play it all together. Some people will call it a cacophonia, but I tell you that after I read this and after I prepared the lecture, I listened to a whole 20 minutes of Ornette Coleman and tried to look for all the different parallel paths that go from one place to another. Thank you for listening. This is about the lecture. I went out of the screen. By the way, my dog even who sits here, my dog is called Richard Feynman III, and he's a beautiful border collie. Richard Feynman II, oh, there's no third yet. And he left the room when he heard the music here. He didn't like it. Okay, if there are something.
Yeah, so we have a nice question maybe from Rafik. So we can give you the parole. So Rafik, do you prefer this, or maybe indeed if
It's only, I don't see any question here, just
you don't see them. So let me see.
Oh, I look at the chat, but there's nothing there.
Yeah, I see an open question, and we can see if I can read it if you want, Rafik. Otherwise, I give you the possibility to speak. What do you prefer?
Question you're talking about?
So the question is, so we know that the electroweak symmetry break is what gave the Higgs potential.
Sorry, Christine, why don't I see it?
I don't know.
It's only to panelists. Do I need to look at another?
Look at the panelists. You know the question and answer below. I can put it maybe for everybody. Let's see. I can do it like this. To everyone, here is the question.
Now I see it. Okay.
Now you can see it, I guess.
We know that the electroweak symmetry break is what gave the Higgs potential. It's Mexican head-shaped generation methods for ensemble. Yet I cannot understand why the electroweak symmetry was broken spontaneously at which moment after the Big Bang this symmetry is not concerned by the yeah. Okay, I'll answer this. Okay, so the breaking of the symmetry occurred probably 1/10 of a billion second after the Big Bang, which is when the universe got cold. When the universe got cold, actually, it's the breaking of symmetry that determines the evolvement of the universe. this is actually what comes out of astrophysics. So this is the connection between astrophysics and the particle physics, if you like. So the breaking occurred about 1/10 of a billionth of a second after the Big Bang. And the thing is that it's exactly how the breaking occurred. And we know the shape that it took, but what actually drove it, it's the cooliness of the universe. And it just like you held a broom on your fingertip. You try to hold it, at some point it will fall down. The same thing that happened there. It was an unstable state, which actually became stable by the breaking of the symmetry, when the universe got cold enough and it could afford it.
So we can see, yeah, if this answer, I think it's very complete. So does it mean that it could have been another universe as well?
Sorry?
Depending, it could have been another universe, depending as well on how.
That's the thing. That's about the landscape. The landscape says that in every universe it breaks in a different way, and that's how you get an infinite number of universes. In each one there are different conditions, and in one of them there are conditions for life, and this is why we ask the question. That's anthropic principle, and we are not even sure that there is another universe like ours. Not at all.
It could not be.
The universes cannot communicate between each other, but if they collide, then there might be created a gravitational pattern by which you will see it. So this is the hope that maybe in the very, very far future, we'll be able to detect some collision of two universes somehow, one with us. I mean, who knows? Somebody wrote here that I'm fascinated by the overtone singing. How does the vocalist suppress lower modes? How would I know if I knew how to do it? It doesn't really suppress them if you listen. It's like, that's why I poured you the Scottish pipe, because it is still there. It's still there. It plays on top of it. It's still there, just like na 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 na. This one, it's the same thing. It's still there, and it plays on top of it the overtones. It's like and it's really overtones. It's duplications of the low frequency. Try to look for tuba throat singers in YouTube, and you'll find this movie and some others.
Yeah, I had seen it before, but the fact is, at the very least, the singer is enhancing the overtones so that you can hear them.
Sure. Yeah. I don't know how. We should invite him. Well, Feynman was fascinated by it.
It's great trick.
Could you comment about symmetry breaking caused by vacuum fluctuations in the Higgs field? Don't know much about that. I'm sorry. I'm an experimentalist. Don't know much about this. How vacuum fluctuations generate the symmetry breaking in here. No, I'm sorry.
And the one above, so by Jeffrey Winkler, so the symmetry breaking was caused by the lowering of temperatures.
Yes. The answer is yes.
That's a fact. The answer is yes. Good.
Actually, before Higgs got the Nobel Prize and Engler, 8 years before this, Engler came to visit a good friend of him in the Hebrew University in Jerusalem. And I called him and said that I'd like to interview him, exactly for the same purpose that I sent this letter to Higgs. And he said, yeah, sure. That was 8 years. That was in 2004. And I said, okay, where should I come? He said, oh, don't worry. I have a rented car. I will come. So he came from Jerusalem to Weizmann. He sat with me for 8 full hours. No lunch, no nothing. And he was so hurt by the fact that the world is calling it the Higgs boson, and that only Higgs gets the credits, etc., etc. And he explained to me the Higgs mechanism exactly from this point of view of temperatures and the Curie temperature and all this. And to tell you the truth, I'm a particle physicist. I found it very non-intuitive to understand. And but he kept on saying it for 8 hours. He explained to me his way of which is non-particle physics, his way of seeing how the mechanism, the Higgs mechanism, is working. And but then he got the Nobel Prize together with Higgs, so everything turned out okay in the end.
It's a combination of expertise, no? Yeah, very good. So do we have any other questions? So by the audience, we can have as well. a question live if you want. So just raise your hand. I think it's yeah, it was really nice as well to finish by the jazz for the added wavelengths as well. That makes this music very universal in one sense. Definitively. So yes, so thank you very much. So I guess that we may one raise hand. Where is the raise hand? Up there. So I allow to talk. Go ahead. Yeah.
Yeah, I wrote this in the chat. What is the perspective on this Roger Penrose's notion of a cyclic universe with the idea that there are so-called Hawking points in the cosmic microwave background data that indicate remnant forms of an earlier universe? And is this idea connected in any way to efforts to develop a quantum theory of gravity?
So the only, yeah, okay. I'm not an expert in this, not at all, but I have some, I know some things about it, so I will tell you what I know. So first of all, the whole book of Stephen Alexander was about cyclic universes because that was his PhD, and the cyclic universes gave him a lot of inspiration about music. So all of his book is about this, but I took it to a completely different story. Now, the idea of Roger Penrose of the cyclic universes is one idea that he's trying to sell right now, but what I know is that the community doesn't buy it. Now, why they don't buy it, I cannot really answer you because I'm not a real expert in this, but they don't buy it, and the experts that I know don't buy it. And it's very complicated. Okay, I tried to read the paper and it's very complicated. So, okay, you know what is cyclic universe, but we want more than that. And more than that, I cannot give you. Sorry. Because I don't understand it too well, this is why I didn't put it in the lecture with the music, because it really goes very well in music. But it's not acceptable. It's a very esoteric idea that he tries to sell.
And we have another comment as well. So Jeffrey Wickler, so in the chat box, if you look at.
Yeah.
That there is no evidence about cold spot.
Trying to see which I had talked with Stephen. Indeed, yeah. We said the collaboration between jazz musicians is similar to collaboration. I have to read it loud. I had a talk by Stephen Alexander, very nice. I would like to hear how it was. Tell me. Where he said that, why don't you speak and tell us this? Tell us about the talk.
So I will allow you to speak.
Yeah, please. I would like to
Go ahead.
Yeah, it was a physics colloquium that was at put on by the University of British Columbia Physics Department. And so we got him to talk, and he talked about different similarities between physics and jazz. He talked about how he first got interested in science because like there was a rap star that rapped about science. Of course, he later found out that the actual science content was inaccurate, but that got him interested in science. But then he talked about he became a jazz musician, and he talked about similarity between jazz and physics. And just one of the things he said is like jazz musicians are like in a jam, and they're like, inspired by what someone said, plays on their instrument. He said it's similar to a group of physicists sort of talking informally, where like someone says something and then someone else almost like is inspired to sort of like riff on the basic idea, and then that sort of leads to them coming up with a new idea in physics or whatever. That was one of the things he said.
So that must have been very fascinating. So he talked about the cyclic universes, didn't he?
No, actually, he didn't mention the cyclic universes. He talked about other things. He mentioned waves in music, but also wave phenomena in different parts of physics. So he talked about like wave phenomena described by physics, but also how that relates to acoustic waves in music. So he talked about that. And he also talked about what you talked about with the Feynman path integral.
Yeah, that I took from him. That's what I said.
Yeah, he did talk about that, sort of relating the Feynman path integral to playing jazz music.
Yeah, okay, thank you. And there is no evidence for the cold spot in the CMB that Roger Penrose predicts. Thank you.
Yeah, I think it was really, really good as well. Again, to finish by jazz, I like it as well. So if we have so no more question or raised hand, so I guess that so have you had still a raised hand, but you had your question answered, isn't it? So R.A. Rosenstein. So I guess so it was the case. So it means that yeah, so we are done also for your great talk, and then the symphony so that came out of the music of the universe. Really interesting indeed, with wavelengths and with having possibility to complete only, I mean, with the visual and then the sound like. So it's really complementary. So it means that even if so you are blind, you could as well be a physicist. So that's a good thing.
Yeah, that's true. Even if you're blind, you can understand the Higgs discovery.
Exactly. Very nice. So thank you so much, so Eliam, so for this wonderful presentation. So we will so see you next week as well to hear more for the statistic and to see how important as well this background is, so that we can discover new scientific result. So from the LHCO, FCC, or any other accelerator that will come into a reality. So then we can just also maybe conclude or finish by the announcement as well for the next so Physics Matters on this so Science for Development series. So we will have on the 24th of August, so at the same time, so the presentations by Harris Westphal, who is the director for the Sirius, so in the Brazilian light source, so one of the observer country, the Brazilian, so will show how those brightest light can just be used as well in South America and impact as well the rest of the knowledge as well that we could get from light source. So I thank you with all of those nice questions as well. We have a few also students so from the African School of Fundamental Physics and Application. So it's really good as well. So we have made as well some links so from the Middle East to the African, so through the American and with European, so let's say. So we're still missing maybe a few Asian, so to be able to participate, and we can really call it international then. So thanks a lot for your attendance, and everything will be so online in a few days, and we look forward to see you. And don't hesitate to send so any question if you want. The email address is up there, and otherwise you see all the link so through the Twitter and then the Facebooks available. So that will be good. And if you have any suggestion and comment, we're more than welcome to tune potentially as well, so our next series as well. So thanks a lot for participating, and looking forward to hearing from you. Thanks a lot, so Eliam, for this great talk, and see you next week.